All right, so today, forgive the sound of the air gun going off behind my head. I'm actually in a different location. We're going to be trying to solve these stoichiometry equations. We're going to go through some one-step equations and some two-step equations, and how are we finding mole ratios, et cetera, et cetera. I know a lot of you who are doing the live sessions, you're watching me type all of this stuff up onto a computer, and that's all fine and good, but there really is something about having a scrap piece of paper next to you, writing out the equation, and figuring it out from there. That's going to make a lot more sense. It's going to be something to consider, especially when we're doing the two-step equations and you're really trying to understand this material. So when we're talking about molar ratios, we're gonna need a balanced chemical equation, which I have for you here. So when I'm asking you to do two-step equations, I'm not gonna be asking you to balance chemical equations because it's just one more step. And I really think that if you haven't learned how to balance a chemical equation at this point, you need to reach out to Mr. Korea or I, and we'll give you extra practice. But when we're looking at this equation, so this is a combustion reaction. We've got a hydrocarbon here, oxygen, and that's going to produce CO2 and H2O. It's balanced for us so we can go to work trying to find mole ratios. Mole ratios are super important to stoichiometry because that's how we determine how much of something we need or how much of something is used. So right here, I'm asking for the mole ratio between this right here, so C4H10, and oxygen. I need to use my chemical equation to solve for mole ratios. I'm just going to erase my lines here this way. I'm starting with a clean slate. So when I look at my chemical equation, for every 2 moles of C4H10, I have 13 moles of oxygen react. So I've got 2 moles of C4H10 over 13 moles of H2. That's as easy as it is. That is a mole ratio.